Yeah, so this was a project that I kind of started a couple years ago and presented kind of a preliminary thing at the last planetary data workshop, but it's kind of a project I've been working on kind of on the side. So I guess I've done some updates since then. So I guess that's, if you were there, maybe a lot of this will seem familiar, but it was a couple years ago, so maybe you'll have forgotten. Yeah, so this kind of started out as a project where we didn't really like what we were currently doing with our color shaded reliefs, and we wanted to see if we could try and improve that in any way. Just in general, color shaded reliefs are really useful. The shading allows users to visualize all sorts of topography, and then the color lets you do some sort of preliminary interpretation. So here's INA D. Can't even really tell that INA D is here. But once we add the shading and the color, we can kind of see all the little mounds. We can tell there's some sort of elevation variation there. But I think it's also important to realize what color shades are not. I would argue that they are not mission critical, unlike the Sporkin et al. Paper where they were looking at medical interpretation of various like veins. No one's lives are probably going to depend on these NAC DTM color shades. I'm hoping if someone does any actual mission planning, they're going back to the slope maps, going back to the DTMs, and not using this kind of intermediary product that's really designed for kind of exploring the data. And I think it's also important to remember that color shades are not representative of some sort of non-sequential, non-continuous data. Say something like a population map or an election map. It really does generally represent something that goes from a lower elevation and gradually goes up to a higher elevation in some sort of continuous fashion. And then kind of the third point I want to point out is that they're not just color maps. They're not just like one color. There's kind of variation in there provided by the shading. And these two things kind of have an effect on what kind of mapping that we choose later. So, okay, here are our current LROC NAC DTMs, which we are desperately trying to replace. They're your very classic rainbow, which anyone who's ever looked up anything on color theory knows is like the worst way to represent analytic data. Right now, they're evenly divided, which is a pretty standard way of doing color maps, but sometimes this has problems. For example, here, equal divisions puts roughly half of our color map in this like relatively insignificant crater. This is a DTM of an Arago imp, which is kind of the small feature that people think may be young volcanism. There's actually over here. So that's one issue. And then when we're evenly dividing the bins, the numbers also get a little difficult to interpret. So how big is this bin size? Well, it's 63 meters. So, and then again, because it's a rainbow, it has all the like perceptual problems where like yellow can show up as false contours. And if you're color vision deficient, this may just be garbage and you will not be able to interpret this map. So this image shows the DTM of the part of the Apollo 16 site, and then it also kind of shows like what this would look like in kind of the three most common types of color blindness. So you can see that like the colors don't match, there's kind of all sorts of variations in brightness. So these are the things that we're trying to fix. So this is kind of the criteria pool that I'm looking at. So if we want to avoid kind of the problem with the even binning on some things, and we want to emphasize topography and various features, which was kind of a criteria handed down to me from my PI, Mark Robinson, where we might have to do something like uneven bin sizes. But I don't want to like sit down and do this for the like 600 plus DTMs that we have of the NAC DTMs. And if we're going to have uneven bin sizes, I especially want nice round numbers so that people who are looking at this can immediately tell that A, the bin sizes are uneven, but also kind of do the math in their head a lot more easily. So those are our kind of main criteria for the custom binning. And then we can get into all the color map stuff. So if we're going to do uneven bins, then it has to be discrete, because uneven gradients sounds like chaos to me. No one can tell what's going on. And the bins need to be easily distinguishable so that you can look at the color, go back to the legend, and understand how big that a range of elevation that represents. It should be relatively perceptually linear. So this means that it is going to change in both like hue and brightness at kind of a linear scale. We don't want to like have this sudden jumps in brightness, like with the yellow and the teal in the earlier map, that kind of makes it look like a false contour and kind of overemphasizes part of the topography. And then we want this to be sequential because, you know, elevation has a low point, it has a high peak point, and we want it to kind of go in between those two. It's not some sort of qualitative data set, and it's not a diverging data set. You know, there's not really like a sea level that we're worried about. And then there's kind of some things that come up with the hillshade, because there's hillshade and there's some shadowing in there. We want to avoid anything with really dark colors that could be confused with both no data, which is represented by black in our color shades, and then shadows, which are going to appear dark. And especially if colors are similar to each other in hue, we don't want the shadows to make it difficult to interpret. And then obviously it would be nice if those with color vision deficiency could easily interpret and it made sense and it wasn't all over the place. And then there's kind of the like nice qualitative things, like be nice if it was pretty, be nice if it was easy to look at for a long period of time, wasn't like overly bright, that kind of thing. So let's talk a little bit about what we've decided to do for the custom binning first. So I kind of looked all over the place and I finally stumbled upon this kind of short little 3-page abstract by M. Eisman, G. Albuquerque and M. Magnor from 2011 called Data-Driven Color Mapping. So what that's really trying to do is it normalizes the elevation values or whatever other data that you're mapping between roughly 0 and 1. And what it's really trying to do is decrease the number of colors where there are large value ranges with a very few pixels. So things like steep slopes and the bottoms of small, deep craters. But it's going to keep values that are very different from having two similar colors. So it's kind of fighting between like making large values more similar and making similar values more different. And then to complicate this, you can actually use this kind of scaling parameter alpha to take this like normalize between 0 and 1 and kind of either skew it so that you're doing more of a histogram equalization if you approach 0, and then more of an equal distribution of your elevation if you give it a parameter of 90. So to get into the math a little bit, so the first is you create a sorted array of all your non-null DTM values. And then you basically make like a 2x(n) matrix where the X value is this index value, like where it is in the array, and then the Y value is the actual elevation value. And then you calculate this V diagonal parameter, the maximum non-null value minus the first one, and then you normalize it by taking the dot product with every element in this 2x(n) array and dividing it by the norm. And then if you want to introduce this, and this will, at this point, you're basically at an alpha equals 45 and everything is going to be normalized nicely between 0 and 1. But you can also add in this alpha parameter by kind of replacing the X value with the difference in elevation divided by the tangent of this alpha parameter. kind of tries to do that balance between emphasizing the topography, but still representing the data by doing that fighting between large ranges of elevation and small, large areas with a small range of elevation. But now, oops, go back, back, sorry. But now we want nice round bin numbers. So if we just do this, we're gonna get all sorts of crazy bin sizes with all sorts of crazy numbers. So there might be an algorithm out there to do this, but I just kind of wrote my own. So the first thing I do is I populate an array of elevations based on just like evenly dividing that normalized output. And then I look at the range of elevation, like how big are those current bin sizes based on that even division of the normalized output. And then I try and determine just from this preset list of options of kind of easily like calculated numbers, what's the minimum bin size? And there's a couple of constraints on that. The big one being like we can't have a minimum bin size that's larger than if we took the whole elevation range and we divided it into equal sections, right? Because otherwise you're just going to keep trying to adjust it to something and you're never going to get to a solution where everything is at least the minimum bin size. You just don't have enough values for that. And then the second constraint I added is in order to make my legends legible, I had to put like a 2% of the elevation range limit on the minimum bin size. And if you add enough colors, sometimes you run into the problem where like you can't get a minimum bin size that both lets you have that 2% elevation range and is larger than the average bin size. But most of the time it works out fine. So the next step is to find a streak of bins that are smaller than the minimum bin size, and then find the center of each of those streaks. And then you add either that center bin to just like a stack, where it's like first in, first out. Or if it's an even set of bins, so you have 4 bins, then you add the center 2, so bins 2 and 3 to the stack. And then you add whether you want to adjust it downward, you like want to lower the minimum elevation of that bin, or upward, you want to raise the maximum elevation of that bin, or if you want to go in both directions, you want to kind of split the difference of adjusting that bin. And then once you have this kind of preliminary stack, you can kind of go through it. As you pop one off, you check, am I raising or lowering? You adjust that bin, and then you check the neighboring bin. Did I make that too small? Is it now less than the minimum? If so, then you attach that to the stack and continue. And if you hit the minimum or maximum elevation, you obviously want to preserve those values. So just preserve the value and then you switch the adjustment direction. And that seems to have worked out pretty well. And then once I've done all my adjustments, the numbers are still not great, but then I can round it to the multiple of the minimum bin size because they're all kind of distributed at least that minimum bin size. The rounding seems to work out really well at that point. Obviously, I'm not rounding the minimum and maximum. So this is just a couple of examples of the results. So this is an equal binning of that same Arago crater DTM with the IMP. And this is kind of the results of the dynamic binning. So you can see the bins do get really dramatically large. In this case, most of the elevation is like down in this like kind of little insignificant crater, just like it was with the even elevation bins. But now it's just one color. Don't really care about it. Sometimes the results are a little bit different. One could argue that because these are even, it might be easier to interpret this, but this doesn't actually give us that much less information. It's just emphasizing some more details in some of the flatter areas. And this is what it looks like when you kind of go through a full range of adjusting these different alpha parameters. So this is kind of the extreme where we're doing histogram equalization. You see like almost this entire mound is like a bright red. Kind of all the way up to what should be roughly even bin sizes. Because I'm enforcing that rounding of the bins, it doesn't always end up exactly even, and I should probably go back and like kind of deal with this as a special case. So we actually, well, my colleague Madeline actually looked at a majority of them, but we looked at over 600 DTMs, and we found that except for like 1.3% of the time, just the default with alpha equals 45 works well. We get a lot of definition in some of the flatter regions, but we're not washing out the maximum peaks too much. So I was going to do a thing where I tried to look at all the histograms of both the slopes and the elevations, looking at all the different elevation ranges. And I did do that for the things that didn't work, but there was not a real pattern. And I think it really comes down to the fact that it depends on what you want out of the DTM. Like, why does the DTM exist? Is it because there's a scarp here? Is it because there's like a certain crater that we care about and the rest of it is just mare around it? So I could probably throw some sort of machine learning at it, but because it's only 1.3% of the time, which was like, I don't know, like less than 20, it was like roughly 20 DTMs that didn't really work. It only takes about a minute, or okay, it takes more like 3 minutes on really large DTMs to run. I think we can just decide if it looks terrible, we'll rerun it. So that was going to be a whole big investigation that kind of got curtailed because it didn't really matter. So that's the binning side of things. So let's talk color maps. This is our current preferred color map. It's kind of an expanded version of a divergent color ramp that is perceptually more or less linear from colorbrewer2.org. This one currently has 17 distinct shades. We found after adding more than 17 between this minimum and maximum value, you start to kind of lose definition. There's like a small possibility we could add like a slightly darker shade at the top or the bottom, but again, we don't want to go too dark because down in the shadows, it's going to get difficult to interpret. So this is just the same exact color scale in gray. So you can see that it's not exactly a smooth curve, but it is at least like relatively sequential, although it is divergent, which I think some people have qualms with, but we found that for these discrete bins, it helps to have more shades, especially if you're going to look at the color and then go back to the legend. The more distinguishable the colors, the better. So I know I'm going to get this question, what about the Matplotlib, Veridis, and Plasma, and some of the other kind of standard color mappings that are available in Python? So this one right here is Veridis for green. This one's Plasma. I decided not to look at Magma and Inferno just because their lower bins are very, very dark. And Plasma is relatively similar. So we showed these to a few people, and they kind of had the same qualms that I do, which is like, it's actually pretty difficult to figure out where the bins break out. And then it's also difficult to just like look at a bin and then kind of go back to the color ramp and figure out, wait, what elevation is this? You have to do a lot of counting. And because we're doing this uneven bin size, we wanted it to be as easy as possible to interpret. So we've kind of ruled those out, but I wanted to show them to you so that you could kind of see where I'm coming from, I guess. And if any of you want to read more about the default matplotlibs, I've included a link here, and I'll share this slide afterwards. And it's like a great article with like their whole like presentation about their new default colors. And I think they're actually really great color schemes for most applications, but because we're doing this kind of weird uneven bin sizing, and because we're kind of combining it with these hill shades, which kind of complicate things, it's not ideal for our situation. And I know people are, again, we've already complained about rainbows and how they're difficult to interpret. But Google has come up with this turbo color map, which is actually relatively perceptually linear. If you look at this, you can see there are some kinks in this curve. And if you stare long enough at the gradient, you can start seeing there's like some slight contours. But this is maybe like our backup one that we're considering. If for no other reason that we should be able to add more colors in here, which might satisfy some of some of the critiques we've had about the original one, which there's not enough colors, there's not enough detail. I think this one is really bright and might be hard to look at after a while, but I do think if you decide you really need a rainbow for some reason, this is actually a really cool rainbow that kind of avoids a lot of the problems. If you, it does the same thing ours does, where like it starts dark and it gets bright and then it goes dark again. But unless you're completely can't see any color at all and everything is gray, then this is actually still appropriate for those with color vision deficiency. And it avoids a lot of the contouring problems. So I'm kind of keeping this in our back pocket, and I kind of love the controversy over rainbows, and especially now that I've thrown this into the mix, I'm kind of interested to see what people's opinions are. But yeah, that's another one. So let's just kind of check back in, looking at our criteria. The custom busing does emphasize topography and various features. It is pretty automated, except for those kind of handful of cases where the default isn't great. And then we need to put more time into that. And it does end up with nice round numbers for the bin sizes. And then going back to the color map, it's discrete. The one that we've chosen is discrete with pretty distinguishable bins. It's relatively perceptually linear. It's not exactly linear, but it is at least continuous enough that it should be interpretable for everybody. And it's also sequential. So it starts, you know, dark blue, ends up red. Yes, the like brightness is diverging, but overall, it's mostly sequential. Avoids really dark colors that can be confusing. It's interpretable for color vision deficiency, unless again, you can't see any color and everything is grayscale. And I think it's relatively pretty. In general, people have preferred this even over the turbo. Even over some of the other color maps that we've tried. And because this kind of avoids those neon colors, it is kind of pretty easy to look at for a period of time. So I know I talked really fast, but that's kind of where we're at with the project. So I'm really interested in people's feedback, because I know there's like a lot of opinions about color maps. So thank you so much.